Good afternoon, students. In this video lecture, we will be discussing about an advanced form of nodal analysis. In the DC nodal analysis lecture, we had discussed the concept of nodal analysis in the presence of current sources, voltage sources, and in the presence of reference nodes. So we'll have a quick recap of what do you mean by a reference node. By reference node, it means there is a presence of voltage source in between a node and the ground potential. If such a case arises where there is a presence of a voltage source present in between a node and the ground potential, then that node is called as the reference node, and the value of that reference node is equal to the value of the voltage source with the sign which is closest to the node. So this concept of reference node has already been discussed in the DC nodal analysis lecture. In this video lecture, we shall be discussing about the nodal analysis in the presence of the voltage source that are placed in between two non-reference nodes. I'm repeating it again, two non-reference nodes. Now one is already familiar with the term called as reference node. So what do you mean by this term non-reference node? Any node which is not a reference node is called as a non-reference node. Now for our understanding, there is a circuit present over here. As we can see, it has got three nodes, one at V1, other at V2, and the third one at V3. Could we find any reference node present in this given circuit? Yes. As we can see, this node V1 is a reference node. Why is it so? Because there is the presence of a voltage source in between the node and the ground potential. Hence, V1 is called as a reference node. And what will be the value of V1? The sign of the voltage source which is closest to the node is plus. So V1 will be assigned plus 10 volts. This is how we assign a particular value to the reference node. There again, in the previous lecture, I had discussed one important hint about this reference node, and I would like to repeat it here once again. Over here in this question, there is only the presence of a voltage source present in between the node and the ground potential. What if there had been a resistor in series with that voltage source? So, with the presence of this resistor R along with in series with the voltage source, will this node V1 be still called as a reference node? No. It won't be called as a reference node. For the node V1 to behave as a reference node, there has to be a presence of a voltage source only. Any presence of any other element in series or in association with the voltage source will nullify the V1 to be called as a reference node. I hope this part is clear. So if any node does not satisfy the condition of a reference node, it is called as a non-reference node. Let us see the nodes V2 and V3 and check them out whether they are reference nodes or non-reference nodes. Now coming to the node V2. Now is a voltage source connected to V2? I cannot find any voltage source connected on the left hand side. I do not find any voltage source connected in the downward direction as well. But yes, I could see a voltage source present on the right hand side of V2. So it means if this voltage source is connected to ground, then V2 can be called as a reference node. So let us see whether this 5 volts is connected to a ground potential or not. Unfortunately, this 5 volts is connected to another node which is V3. And V3 is not at ground potential. Hence, V2 does not qualify to be a reference node. Rather, V2 is a non-reference node. A node can be called as a reference node if it is connected to a voltage source, and that voltage source is eventually connected at the ground potential. Only in that case, a node would be called as a reference node. Under no other circumstances, a node can be termed as a reference node. Since V2 is not satisfying that criteria, it is called as a non-reference node. Let us check for the node V3. Now, as you can see, V3 has got 3 branches connected to it. There is no presence of voltage source in the upward direction. There is no presence of voltage source in the downward direction as well. But yes, there is a presence of a voltage source in the leftward direction. Now, if this potential or the voltage source is connected to ground potential, then V3 would be termed as a reference node. Unfortunately, we can see again that this 5 volts is connected to node V2, and this V2 is not at the ground potential. So V3 eventually does not qualify to be a reference node, and it is also coming under the category of non-reference node. So we had 3 nodes asked in this circuit or being picturized in this circuit. They are V1, V2 and V3. V1 came out to be the reference node, whereas V2 and V3 are termed as non-reference nodes. So what is our topic of discussion today? We have to carry out the nodal analysis in the presence of voltage source present in between 2 non-reference nodes. So by this time, we already know what is the meaning of non-reference node. V2 and V3 are together termed as non-reference nodes. So is there any voltage source present in between those 2 non-reference nodes? Yes, we can see a voltage source present in between those 2 non-reference nodes. So when you have a situation like this, how to carry out the nodal analysis under such circumstances? And this particular situation or condition is called as a supernode condition. I'm writing it over here. It's called as supernode condition. Now there again, there is a hint over here as well. As we had discussed, for a reference node to be called as a reference node, there should be no resistor in series with that voltage source. Otherwise, the node won't be a reference node at all. Similarly, if we are coming across a condition such as supernode, then there has to be the presence of a voltage source in between 2 non-reference nodes. I repeat it again. For 2 nodes to form a supernode, there has to be a presence of a voltage source only in between the 2 non-reference nodes. If there is a condition where V2, which is a non-reference node, it's connected to a voltage source that has a resistor in series, and finally it is connected to V3. And let us assume the remaining circuit to remain the same. In that scenario, this V2 and V3 are certainly non-reference nodes. However, there is not a presence of voltage source only in between these 2 non-reference nodes. There is a presence of resistor as well in between the 2 non-reference nodes. In such a scenario, V2 and V3 do not form a supernode. In order to form a supernode, there has to be the presence of a voltage source only in between the 2 non-reference nodes. Then only we can say that it is a supernode condition. I hope this part is clear. What is a reference node? What is a non-reference node? When do we have a supernode condition? And when we do not have a supernode condition? So based on this supernode condition, we are going to solve 2 numericals today. So let us begin with the first numerical. Now this is our first circuit. In fact, we had used this circuit in our first slide to understand the concept of supernode. Now the question says one is required to find out the values of V1, V2 and V3 using nodal analysis. The concept of nodal analysis is already clear to us. In the concept of nodal analysis, we have to consider one node at a time, and that node is to be assumed to be at higher potential. As it is assumed to be at the higher potential, the current always flows in the outward direction. However, in the presence of a current source, the direction of the current source is taken into consideration. So these basic concepts are already clear to us in our DC nodal analysis video lecture. So let us now begin with the steps. What is the first step? The first step says identify the nodes. The nodes are already identified. They are V1, V2 and V3. So in all there are 3 nodes. 3 nodes implies that there are 3 unknown variables. So one must have 3 equations in order to find out these 3 unknown variables. Now the second step says find out if there are any reference nodes present in the circuit. So are there any reference nodes present in the circuit? Let us check. First we shall work out with V1. Is V1 connected to any voltage source? Yes. Is that voltage source connected to ground? Yes. So V1 is called as a reference node. So what will be the value of V1? The sign of the voltage source which is nearest to the node V1 is plus. So V1 is assigned as plus 10 volts. Let us now check with the node voltages V2 and V3. Now we had already checked in our first slide itself, and V2 and V3 had come out to be a non-reference node. In fact, V2 and V3 were forming a supernode. Now, is there any advantage of having a reference node in the circuit? Yes, it certainly has an advantage. The advantage is, when we started with our analysis, we figured out that there are 3 nodes. 3 nodes means there are 3 unknowns, which implies we need to write 3 equations in order to find out all the 3 values. However, the moment we figure out the presence of a reference node, the value is immediately known to us. In that case, the number of unknowns gets reduced by the number of reference nodes that are present in the circuit. Say for example, in this case, currently the number of unknowns are 2 and they are not 3. It's because we have already obtained the value of V1. Now our objective is to find out the value of V2 and V3. So let us start writing the nodal equations for V2. Now nodal analysis means the application of KCL. For the application of KCL, one has to figure out the number of branches that are connected to a particular node. The number of branches is equal to the number of terms present in the KCL equation written for that particular node. So we will be writing the KCL applied at node V2. So how many branches are there for V2? There are 3 branches. So one must have 3 terms in the KCL equation. And as it was already discussed in the previous video lecture, if for any chance one is not able to write the KCL equation for any branch, in that case the KCL equation cannot be written. Now before we start writing this KCL equation at node V2, one must recall one most important thing, that KCL can be written in 2 variants only. One is in the form of I. If the current source is available to us, then the value of the current source will directly give us the value of I. And the other form is V upon R. I can be written as V upon R. Normally, in the absence of the current sources, the widely used expression is V upon R. So these are the 2 ways in which we can write the KCL. There is no other way to it. At the same time, the number of branches should be equal to the number of terms in the equation. If for any chance one is not able to write the equation for a particular term in the KCL equation, then the equation for the term cannot be written and one has to drop that. So these are the 2 important things that we have already studied in our previous video lecture. So let us start writing the KCL equation at node V2. Now V2 is connected on the left hand side to node V1. So the KCL equation for this branch can be written as V2 minus V1 upon 2. Our assumption is the current is always flowing in the outward direction. Based on this assumption, the equation for this term or this branch has been written. Plus, since all the currents are moving in the outward direction, KCL says summation of all the currents meeting at a point is equal to 0, or summation of the currents coming is equal to the summation of the currents leaving. Coming to the second branch that is flowing in the outward direction. It is once again connected to a resistor. Finally, it is connected to the ground. So it can be written as V2 minus 0 upon 8. So we have already written the equation for the two terms. We are left with the third one. So let us move on with the third one. Now V2 is connected to a voltage source and finally it is connected to V3. So how will our equation be? We have to start from V2. Why? Because that is the node for which the KCL is being written. So it is assumed to be at a higher potential. Our direction of writing the equation is from left to right. So we start with V2. When we are traversing from left to right, what is the last sign encountered for this 5 volts? It is minus. So it will carry a minus sign. Finally, what will be the sign carried by V3? In nodal analysis, when we are writing the KCL for a particular node, it is assumed to be at a higher potential. At the same time, all other nodes present in the analysis are assumed to be at a lower potential. So it will be written as minus V3. So we are done with the numerator. What will be the value of the denominator? It has to be in the form of V upon R. Is there any R present in this particular branch? That's a very big question. Do we have any resistance present in this particular branch? If there are none, then what is the value of R? R is 0. And with this, we have written the equations for all the three terms. And this is now equal to 0. Now the question is, this is a valid form of V upon R. This is a valid form of V upon R. Is this valid? No. The presence of a 0 in the denominator makes the entire term go indefinite. Hence, the value of this term is not known to us. So it implies that one cannot write the KVL equation for this particular term or for this particular branch. Hence, as we had previously concluded, the KCL cannot be written for this branch. So what is to be done in such a scenario? When one is not able to write the KCL equation due to the presence of 0 resistance in a particular branch, it implies that we are dealing with the supernode condition. I hope this part is clear. So let us see now how do we solve this condition of supernode. I have redrawn the circuit once again for our reference. Already with the help of the reference node concept, V1 has come out to be 10 volts. We are presently working to figure out the equations for V2 and V3. We figured out that we cannot write the equations for V2. Now the question is, can we write the KCL equation for V3? There are 3 branches connected to V3. I can write the KCL equation for this branch. I can write the KCL equation for this branch. But can I write the KCL equation for this branch? I'll encounter the same situation that I had encountered for V2. For this place, it will come out to be V3 because I'm traveling from right to left. So V3 plus 5 minus V2. Minus V2 because V3 is assumed to be at higher potential and we are writing the KCL for V3. Naturally, V2 has to be at a lower potential than V3 upon 0. Again, that indefinite condition is coming into the picture. So one cannot write these type of terms in the KCL equation. So let us now see how to write the supernode equation. Now by the term supernode, one can mean it is a bigger node. Super, so it's a bigger node. When one encounters a condition of supernode, in that case, one has to consider V2 and V3 as one node. I'm repeating this part once again. The supernode condition has been seen in between the node V2 and V3. So, V2 and V3 together shall form a supernode, which means together they will form a bigger node. Earlier, we used to write the KCL for one particular node. However, under a supernode condition, we have to club the equations of both the nodes forming a supernode. I'm writing that part over here. Club the KCL equations of two nodes that form a part of the supernode. So in our question, V2 and V3 form a supernode. So one is required to club the KCL equations of the branches connected to V2 and of the branches connected to V3 and form one single equation. So how many branches are connected to V2? They are 3. However, one branch is a supernode branch. So what can I write for V2? For V2, there are 2 branches for which the KCL can be written plus one branch which is a part of the supernode branch. Likewise, for V3, there are 3 branches, 1, 2 and 3. So there are 2 branches for which the KCL can be written, and again there is one branch which is common to the supernode branch. So when we are going to club the KCL equations of the 2 nodes, so how many terms will be present in that KCL equation? The number of terms that will be present in that KCL equation would be 4 terms by clubbing V2 and V3 together plus 0. Why is it 0? Because we cannot write the KCL equation for that supernode branch. I am writing SN, in short supernode branch. So is this part clear? There are 2 branches for which KCL can be written. They are associated with the node V2, and there are 2 branches associated with V3 for whom the KCL equations can be written. So now when we club the branches by taking V2 and V3 as a supernode, the number of terms present in that supernode equation would have 4 terms. Now let us write and check it out. How would the equations look like? Let us write first the 2 branch KCL equations associated with V2. So there are 3 branches. We will drop this supernode common branch. We will write the equation for this branch and for this branch. Yes, one more thing. The conditions of the nodal analysis remains the same for supernode condition as well. The node for which the equation is to be written is assumed to be at higher potential and the current is flowing in the outward direction only. The only difference created over here is one cannot write the KCL equation for that supernode branch. Hence, all the branches associated with the supernodes have to be clubbed together and one single KCL equation is to be framed. So let us write down the equation for the branch connecting V2 and V1. It can be written as V2 minus V1 upon 2 plus. All the currents are assumed in the outward direction. So it's a plus. V2 minus 0 upon 8. So these are the 2 equations for the node V2. Now one is required to write the branch equations for V3 as well. So let me write down the branch equations for V3. Again, V3 has got 3 branches, one in the upward direction, one in the downward direction. the left-hand branch equation can't be written because it forms a part of the supernode branch. So let me write down the equations for these two branches. The current is assumed to be in the outward direction. So it will be again a plus because we have to club. So let me write down the equation for this upward branch. It can be written as V3 minus V1 upon 4 plus V3 minus 0 upon 6. So these are the sets of branch equations associated with node V2, and these are the sets of branch equations associated with V3. What does supernode condition states? It states that one has to club the KCL equations of the branches together in case the two nodes are forming a supernode. So how to club them? The sets of equations of V2 are known. The sets of equations for V3 are known. Add them together, which means club them together. And finally, equate them to 0. So this in total represents the KCL equation for the branch or for the nodes that constitute a supernode. Is this part clear? So this is how we can write the KCL equation for the supernode condition. Now there were three unknowns. We already figured out the value of V1, so we are left with two unknowns. We have already obtained the supernode KCL equation. Now we are still left with one more equation. Where do we get that final equation? We have wrote the equation for all the branches present in the circuit except one. Can you figure out which is that branch? The branch is this supernode branch. And one already knows that the KCL cannot be written for this branch. However, can a KVL equation be written for this branch? Yes. Due to the presence of a voltage source only between the two non-reference nodes, instead of framing a KCL equation, a KVL equation can be framed. And that forms the third equation of the circuit. Now how can one write the KVL equation for that particular branch? Now let us look into that. Here it is a V2, over here it is V3, and one has to write a KVL equation for this particular branch. Let us follow the principles of writing the KVL equation starting at V2 and ending at V3. So V2 is assumed to be at higher potential, so I can write V2. Since our analysis is from left to right, so what is the last voltage sign encountered by us? It is minus. So it is minus 5. Since V2 is at higher potential, V3 has to be at a lower potential. So it is minus V3. We have included all the voltage terms. Can we equate this to 0? Yes. And this is our KVL equation for this branch called as a supernode branch. And this is how a KVL equation for a branch is generally written. At this point of time, one must be wondering, why did I start writing the KVL equation from V2? Why not write it from V3? It is possible to write the KVL equation starting from V3 as well. If you are starting at V3, it means V3 is assumed to be at higher potential, and naturally V2 will come out to be at a lower potential. And what is the direction of analysis? We will be moving from right to left. So what is the last sign of the voltage source encountered? It is plus. So it is plus 5 minus V2 is equal to 0. Either we start writing the KVL equation from V2 or from V3. Both these equations will give us the same structure. There is no difference in both these equations. That is the fineness of assuming a particular node at a higher potential while carrying out nodal analysis. And of course, the assumptions that we have studied in our DC mesh analysis as well. These assumptions studied either in DC mesh or in DC nodal actually help us in writing equations for any type of circuits given to us. So now we have our three equations present with us. The first equation is already solved because the value of V1 is directly obtained as 10 volts. Now we are left with two equations. One is for the supernode equation and the other equation is the KVL applied at the supernode branch. Let us solve these two equations and find out the values of V2 and V3. This is the first set of equation. I'm rewriting both the equations over here. Upon simplification, it comes out to be, in this equation, the value of V1 has been substituted as 10 volts. Upon further simplifying, this comes down to 15 times of V2 plus 10 times of V3 is equal to 180. And there is a KVL equation as well, which is V2 minus V3 is equal to 5. So these are the two sets of equations. So one has to solve these simultaneous equations using your calculators. Please make sure that whenever you are dealing with the equations, do remember to write the variables in their correct order. V2 has to be written first, followed by V3, and the same pattern is to be followed for every set of simultaneous equations. You can even consider V3 to be first, followed by V2, but V3 has to carry its own coefficients, followed by the coefficients carried by V2. And always make sure that the constants are on the right hand side of the equations. So solving these two sets of simultaneous equations, one can obtain V2 as 9.2 volts and V3 as 4.2 volts. And V1 is already known as 10 volts. So this is how one can solve for V1, V2, V3 using nodal analysis in presence of a voltage source which is present in between two non-reference nodes. Or this is how one can use nodal analysis in a supernode condition. Let us solve the next example, which is a very important question, but the basics are still the same. Once you know the basics means you can solve any type of question being asked to you. So let us move on to the next question. So this is our next question. So what does the question says? The question says find V1, V2, V3 and V4 using nodal analysis. As you can see, this is V1, V2, this is V3 and this is V4. Before we begin with this question, we must figure out whether this is a supernode question or not. Is there a voltage source present in the circuit? That is the first thing one has to look for. Yes, I can see there are two voltage sources present in the circuit. One is 6 volts, another one is 8 volts. The second question is there a presence of reference node in the circuit? Yes. The 6 volt source is present between a node and the ground potential. So definitely this V1 is a reference node. So V1 will be equal to, this is the plus sign and this is the minus sign. So the positive sign is closest to the node V1. So V1 will carry a value of plus 6 volts. Now let us look for the remaining voltage source. Is this voltage source connected to a node? Is making the node a reference node or not? Now this 8 volts is connected to V4 and V3. Are these V4 or V3 connected to ground potential? No. Which means V3 and V4 are non-reference nodes. And there is a presence of a voltage source of 8 volts in between V3 and V4. So it means this is a question of supernode condition. And one is required to solve this using nodal analysis. That's what the question is asking us to do. So how many unknowns are given to us? There are 4 unknowns. However, the value of V1 is already known as it is a reference node. So we are left with 3 unknown variables, out of which V3 and V4 form a supernode. So we can write a direct KCL equation at V2 since V2 is not a part of the supernode. So let us first write the KCL equation at V2. So this is V2. How many branches are connected to V2? There are 3. As there are 3 branches, the KCL equation will have 3 terms. Let me write the KCL equation starting with the left side branch. So it will be V2 minus V1 upon 4. So we are done for the left side. Let us write the KCL equation for the downward branch. Now this downward branch has a current source in series with a resistor. Now whenever there is a current source in series with a resistor, this resistor becomes redundant. By redundant, it means there is no requirement of this resistor to be present. Why is it so? Even if this resistor is not present, the current flowing through this branch would remain 2 amps only. As 2 amps is a current source, the current would neither increase nor decrease. So the presence of this resistor is not going to affect the value of this current source. Hence this resistor is termed as being redundant. So this 2 amps is the value of the current which we will be considering for our KCL equation. Now what is the direction of this current? It is not in the outward direction. It is actually flowing towards the node V2. So it's in the opposite direction. So it will carry a minus sign. -2. And I'll only write 2 because it is a current. The KCL can be written in two forms only. One is I, the other one is V upon R. Now moving on to the last branch connecting V3, it will be V2 minus V3 upon 10. 3 branches, we got 3 terms for the KCL, so equate it to 0. So the KCL equation for the V2 node has been written down successfully. Now one is required to obtain 2 more equations because there are 2 more unknown nodes available or unknown variables present in the circuit, V3 and V4. As V3 and V4 are forming a supernode, we know what are the sets of equations to be written. The first set is, one has to consider V3 and V4 as a supernode, that is one node, and write the combination of the KCL equations forming due to V3 and V4. And the second equation is to write the KVL equation for this supernode branch. So let us begin with the KCL equation that we are supposed to write by clubbing the branches of V3 and V4 together. How many branches are connected to V3? There are 3. So what will I write over here? For the node V3, there are 2 branches for which directly the KCL can be written, plus there is one branch which is common to that supernode branch. Likewise, find out how many branches are connected to V4. This is the first branch connected to V4. Over here, there is a 0 resistance path. So one might say that this is the second branch. However, since this is a 0 resistance branch, you cannot consider this to be a connecting branch. You have to eventually reach the ground. One cannot write the KCL equation for this branch. Why is it so? Because this node is at a potential of V4. And what is the potential at this node? It is again V4. Why? Because it is a short circuit path present in between. So how can you write a KCL equation connecting the same nodes? You can write the KCL equation only when there is a flow of current, because KCL means it is a current law. There has to be a flow of current. If it is a 0 resistance path, so none of the potentials are at the higher end or at a lower end. So can you write a KCL equation connecting V4 to V4? One cannot. Why is it so? Because for KCL, one has to assume one node at a higher potential and the other node at a lower potential. Just because we assume one node at a higher potential, the current always flows in the outward direction with respect to that higher potential node. If both the nodes are at the same potential, in fact, they are of the same value, then how can the KCL be written over here? So one cannot write the KCL over here. Now, is this node branching out to some different branches? Yes, it is branching out to 2 different branches. And the KCL can be written for these 2 branches. So in all, how many branches are connected to V4? It is 1, 2, 3, and this one being the 4th. So it can be written as 3 plus 1. 3 branches for which the KCL can be written, 1 which is common to the supernode branch. So together, the KCL for the supernode branch will have how many terms? it will have 2 plus 3, 5 terms in that KCL equation. So let us write down those 5 terms for the KCL equation. Let us begin with V3. The branch which is connecting V3 and V2, the KCL can be written as V3 minus V2 upon 10 plus the downward branch connecting V3 to the ground potential, V3 minus 0 upon 20. So these are the KCL for branch V3. Let us write down the KCLs for branch V4. Starting with this 20 ohm resistor branch. V4 minus V1 upon 20. Coming down to these two branches, it can be written as V4 minus 0 upon 30 plus this last branch has a current source present in it. So the current value is to be mentioned in the KCL equation. The current source is traveling in the opposite direction of that assumed by us. So it will carry a minus sign. So minus 5. So these three represent the KCL equations for V4. Now one is required to club these two nodal KCL equations together to form the supernode KCL equation. So I'll club them together. So these are the complete set of KCL equations for the supernode branch. Finally, we are supposed to equate it to 0. So with this, we have obtained our second equation as well. Now looking forward to our third equation. Our third equation will comprise of the KVL equation of the supernode branch. Let us start with the V3 side. V3, we are traveling from bottom to top. So last sign encountered for this voltage source is plus 8. Since V3 is at a higher potential, V4 will be at a lower potential, that is equal to 0. Or if you are beginning with the V4 side, it will be V4 traveling from top to bottom. The last sign encountered for the voltage source is minus. So it's minus 8 and minus V3 since V3 will be at a lower potential as compared to V4. And finally equating it to 0. So either of these equations, KVL equations, can be used for our analysis. I'll go with this one. Why do I prefer to go with this one? Because V3, we are assuming our unknown variables in the order of V2, V3 and V4. So if I am considering this equation with V3 first followed by V4, I do not have to rearrange this equation once again. So we have obtained our three sets of equations. I'm writing it down on a fresh page. This was the equation for V2. Upon simplifying this equation, one can obtain, put V1 is equal to 6 volts. Now over here you can see that I have left this space blank. Why is it so? Because there are three unknown variables, V2, V3 and V4. For the equation that was obtained by writing the KCL at node V2, there is no presence of this term V4. But while writing down the matrix values or while inserting the values in the scientific calculator, one has to insert it as 0. If you are not leaving this space as 0, it's very likely that one can commit a mistake by doing something erroneous in this part. So be very careful, either write this as 0 V4 or leave this space blank such that you can understand that V4 is equal to 0 for this equation. Now writing down the supernode equation. So this represents the entire supernode equation comprising of 5 terms. Upon simplification, one obtains. So this is the second equation. Now you might be wondering, why have I written here the coefficient of V2 as minus 6? I could have multiplied minus 1 throughout and could have changed the signs. The thing is, it does not make any difference if the coefficient of the first term is positive or negative. Eventually, one has to create a 3 cross 3 matrix out of these variables V2, V3, V4 and insert these values into your scientific calculators. So whether it is coming out to be positive or negative makes less of a difference. The thing where one should work upon is the accuracy with which one is computing the final values. Now move on to our last equation, which is the KVL equation written for the supernode branch. Let me write here KCL. So this is the third equation. Now, solving these three sets of simultaneous equations, one can obtain the values of V2 as 17.8604 volts, V3 as 27.5116 volts, and V4 as 35.5116 volts. And already V1 is known to us, which is equal to 6 volts. So this is how one can figure out the nodal voltages values using nodal analysis in the presence of a voltage source which is present in between two non-reference nodes. I hope you guys have understood the concept of supernode. Usually the questions asked in DC are not that simple. They will definitely have the presence of a voltage source in between two non-reference nodes. So one must know the technique of solving the nodal voltage values in such a scenario. Practice sets for this concept will be provided in the description below. Solve those practice sets and try to clear your doubts as much as possible. The more you clear your doubts, the better your concepts become. So try to solve as many numericals as you can, apart from the ones that are being provided in the description, of course. Apart from this, if you have any doubts, any queries, then please do let me know. I'll be very happy to solve them, or will be very happy to figure them out for you. So with this, we have solved all the values of the node voltages. Now let us go back to the question. Now in this question, one can see there is this current I mentioned over here in the downward direction. So this question asks us to figure out the value of I in the downward direction. This current I is connected or is flowing through the branch which is connected to node V3. And when V3 is considered to be at a higher potential, the current is made to flow in the outward direction. So the direction of I asked in this question is in the positive direction as of our analysis. So what will be the value of the current I? I can be written as V3 minus 0 upon 20. Now the value of V3 has already been computed. Substituting the value of V3 in this expression of I, one can figure out the final value of I. So let us see what is the value of I. I have noted down all the voltage values that were being obtained by us. The value of I from our analysis has come out to be V3 minus 0 upon 20, and it is positive in the downward direction because our analysis is positive in the outward direction. So substituting the value of V3, the final value of I comes out to be 1.375 amps. So this is how one can solve for the nodal voltages using nodal analysis in the presence of a supernode condition. Supernode condition forms when there is a presence of a voltage source in between two non-reference nodes. I hope with this your concepts are all clear and you have understood how to work out with the supernode condition. Practice questions for the same shall be provided in the description. That's all in this video lecture. Thank you for watching.